Okay, so back in 1928, a physicist writes this down. Just a handful of symbols, right? But what's incredible is that hidden inside this one super elegant line of math was a secret, a prediction so profound it would literally change our entire picture of reality forever. So let's really get into it. Because the real question here isn't just, what does this equation mean? The mind-blowing part is how it forced physicists to accept a totally shocking new reality. The idea that for every single particle of matter, a perfect opposite reflection had to exist. Yeah, this is the story of the Dirac equation. And it's an amazing one. It's really a tale of incredible intellectual courage, of, mathematical beauty, and the discovery of a whole universe. One hidden right in the mirror. All right, to really get where this thing came from, we got to jump back to the 1920s. See, physics at the time was facing this huge fundamental crisis. It was basically a house divided against itself. So, on one side, you've got quantum mechanics, this brand new, super weird theory of the very small. And then on the other side, you've got Einstein's special relativity, the theory of the very fast. Now, here's the problem. They were completely, utterly incompatible. See, quantum theory treated time and space as totally different things. But relativity, it demanded they be part of a single, symmetrical fabric. You can see the issue, right? Physics just couldn't have it both ways. Okay, so the obvious first move was to just, mash them together, right? So physicists came up with something called the Klein-Gordon equation. It was relativistic, it did what they wanted in that sense. But it had a really, really fatal flaw. It predicted something called negative probabilities. And look, that isn't just weird, it's physically meaningless. It makes no sense. It's like saying there's a minus 20% chance you'll find your keys. It's just complete nonsense, right? The whole theory was a total dead end. And then enter Paul Dirac. This guy was a brilliant and famously quiet physicist, and he decided that if the direct path was a bust, he'd just find a completely new one. He wasn't interested in just patching up the old theories. No, he was going to build something brand new, from the ground up, all guided by one single principle. You see, for Dirac, mathematical elegance wasn't just some nice to have, it was his compass. He genuinely believed that the fundamental laws of nature had to be expressed through beautiful equations, and it was this conviction that would lead him to his absolute greatest discovery. So here's the key insight, and this is brilliant. To fix that whole probability mess and keep the symmetry, Dirac insisted his new equation had to be perfectly balanced, what we call first order in both time and space. He then tried to do something that honestly seemed impossible. He tried to take the square root of the main relativistic energy equation. But as he started working it out, he realized something incredible. The only way to make the math work, the only way, was if his coefficients weren't just ordinary numbers. They had to be these special arrays of numbers we call 4x4 matrices. And that was the breakthrough. It meant the electron couldn't be described by a single number anymore. Nope. It needed something new, a spinor, which is basically a column of 4 related values that describe its state. And this purely mathematical requirement, it was about to unlock physical secrets that absolutely no one even knew were out there. Okay, and this is where the story just gets truly incredible. I mean, Dirac set out to solve one problem, right? Unifying relativity and quantum mechanics. But his equation, once he built it, it just started handing out solutions to other huge puzzles in physics, like for free. So take electron spin, for example. Physicists knew it was a thing, they knew it existed, but in the old theories, they literally just had to tack it on by hand, like an afterthought. But in Dirac's equation, oh no, spin wasn't an add-on at all. It just emerged automatically right out of the math. That 4-part spinor structure, it demanded that the electron have spin. It was built right in. And get this, it gets even more stunning. The equation predicted the precise strength of the electron's magnetic field, what's known as its G factor. It spat out a value of exactly 2. And when the experimentalists went and measured it, that's exactly what they found. I mean, think about that. The equation wasn't just describing reality anymore, it was predicting it with absolutely breathtaking accuracy. But the equation held one more secret. And this one was, it was a dark one. It looked like it had the same kind of catastrophic flaw as the theory it was supposed to replace, just for a totally different reason. So remember that 4-part spinor? Okay, so two of those parts describe the electron and its spin, just like they expected. But the other two, well, they described solutions with negative energy. And this seemed catastrophic. It basically implied that every single electron in the universe should instantly spiral down into this abyss of negative energy, just spitting out infinite radiation along the way. I mean, based on this, our universe shouldn't even exist at all. Dirac's solution to this problem was, it was one of the most audacious, imaginative leaps in the entire history of science. He proposed that the vacuum, space itself, isn't empty. Not at all. He said it's completely full, a calm, infinite sea of particles that are occupying every single one of those negative energy states. And because of something called the Pauli exclusion principle, no other electrons can fall in. So our universe is stable. Whew. So this led to the final, absolutely stunning prediction. What if you hit the sea with enough energy, like with a high-energy photon? Well, you could actually knock one of those negative energy electrons out of the sea and launch it into our world. And to us, it would look just like a normal electron. But here's the crazy part. It would leave behind a hole in the sea. And that hole, which is just the absence of a negative charge in that spot, would behave exactly like a particle with a positive charge. So, in 1931, Dirac goes and publishes his prediction of this anti-electron. And then just 1 year later, a physicist named Carl Anderson is studying these photographs of cosmic rays, and he finds a particle track, curving the wrong way in a magnetic field. It had the mass of an electron, but a positive charge. He had found it. He discovered the positron. Dirac's crazy idea about a hole was real. Antimatter was real. But you know what? The discovery of antimatter wasn't the end of the story. Oh no, it was just the beginning. The Dirac equation went on to become an absolute cornerstone of modern physics. And believe it or not, its impact is all around us today. The Dirac equation is the foundation of quantum electrodynamics, or QED, which is hands down the most precisely tested theory in all of science. That antimatter it predicted, we use it every single day in medical PET scans. Its structure is helping us understand the totally bizarre behavior of electrons in new materials like graphene. And it's still pushing physics forward today, inspiring the search for new kinds of particles in fields like quantum computing. It's just wild. And all of this brings us to a final, really profound question, one that was captured beautifully by the physicist Eugene Wigner. Why? Why is abstract mathematics, something we often just pursue for its own internal beauty, so unreasonably effective at describing our universe? Think about it. Dirac didn't discover antimatter by looking through a telescope. He found it by insisting that his math had to be elegant. And the universe, in its own mysterious, incredible way, just agreed.